Hey there, and welcome back to the Sleepless Scientist. Tonight, we're embarking on an extraordinary journey, one that stretches back through immense spans of deep time. We'll explore a world reshaped by ancient forces, a world where magnificent creatures once roamed, ruled, and then vanished. It's a story of life's incredible resilience, of quiet beginnings, and of triumphs etched into stone. Before we dive into this prehistoric mystery, take a moment to settle in. If you enjoy unraveling the secrets of our planet's past, please consider liking this video and subscribing to the channel. Your support helps us keep these journeys going. Our story begins not with a roar, but with a whisper, an echo from a time when Earth itself was recovering from an unimaginable catastrophe. Scientists, like modern-day detectives, sift through clues left millions of years ago, piecing together a puzzle far grander than any human drama. They seek to understand how a world nearly wiped clean could give rise to some of the most iconic creatures ever to walk its surface. Imagine a world teetering on the brink. Around 252 million years ago, Earth experienced the Permian-Triassic extinction event, often called the Great Dying. It was the most severe extinction in our planet's history, wiping out an estimated 90% of all marine species and 70% of terrestrial vertebrate species. The planet was a desolate landscape, a canvas almost entirely erased. What remained was a world of empty spaces, silent forests, and barren plains. Ecological niches once teeming with life lay vacant. This profound emptiness, though tragic, also presented an unprecedented opportunity for the survivors. Life, in its stubborn, persistent way, would find new paths, adapt, and eventually flourish again. For generations, paleontologists have been fascinated by the gap in the fossil record immediately following this event. Dr. Evelyn Reed, a quiet but determined paleontologist, spent years poring over fossil collections, seeking the first hints of recovery. Her initial observations revealed a surprising diversity of small, resilient creatures emerging from the shadows. Among these survivors were various reptilian groups. Not all would lead to dinosaurs, but many were part of a larger evolutionary experiment. Scientists observed a rapid diversification, a reptilian renaissance, as new forms adapted to the changed environment, exploring different ways of life. One particular group, the archosaurs, held a special significance. These were the ruling reptiles, a lineage that would eventually give rise not only to dinosaurs but also to pterosaurs and crocodiles. Their early forms were often small, agile, and deceptively ordinary, blending into the tapestry of the recovering world. Distinguishing these early archosaurs from other reptiles of the time was a subtle art. Their skeletal structures shared many similarities, making identification a painstaking process. Researchers had to look for minute differences in bone shape, muscle attachment points, and the arrangement of their teeth. Much of our understanding comes from places like the Karoo Basin in South Africa, a region rich in Permian and Triassic fossils. Dr. Kenji Tanaka led expeditions there, enduring harsh conditions, driven by the hope of unearthing the earliest chapters of this story. The dry, dusty landscape held secrets millions of years old. His team unearthed fragments of jaws, vertebrae, and limb bones. These fossils, though incomplete, provided critical evidence of early archosaur relatives. The excitement wasn't in finding a complete skeleton, but in confirming the presence of these crucial ancestors in the Triassic period. Each fragment told a part of the story. A particular ankle bone, for instance, known as a crocodilian normal ankle, was a key indicator, allowing scientists to differentiate early archosaurs from other reptilian groups. It was a subtle structural innovation that would have profound evolutionary implications. Beyond individual fossils, researchers like Dr. Lena Petrova worked to reconstruct entire ancient ecosystems. By studying plant fossils, sediment types, and the distribution of different animal remains, they began to paint a picture of the world these early archosaurs inhabited, a world of ferns, conifers, and humid river systems. It's important to remember that at this point, dinosaurs, as we know them, did not yet exist. The Triassic world was dominated by other formidable creatures, large amphibians, early mammal-like reptiles, and imposing crocodile-like archosaurs called phytosaurs. Our future giants were still small, unassuming players on the sidelines. Deep within this mix, among the smaller, less conspicuous fauna, were the true ancestors of dinosaurs. These proto-dinosaurs were often bipedal, relatively small and insectivorous or carnivorous. Their existence was a quiet beginning, a humble origin that belied their future dominance. Identifying these proto-dinosaurs among the myriad of early archosaurs was a monumental task. The lines were blurry, the evolutionary steps gradual. It was like trying to find the very first ripple in a pond that would eventually become a tidal wave. One of the most significant breakthroughs came from the Isquigualasto Formation in Argentina. In the 1960s, a team led by Dr. Alfred Romer began excavating, uncovering a treasure trove of late Triassic fossils. Among them were some of the earliest definitive dinosaurs. Fossils like Aeoraptor and Herosaurus*, though still relatively small compared to their later kin, presented clear anatomical features that distinguished them as true dinosaurs. Their hip and limb structures, in particular, were telltale signs of a new evolutionary direction. The key lay in their hip structure. Dinosaurs evolved a unique pelvic arrangement where the femur fit into a fully open hip socket, allowing them to stand with their legs directly beneath their bodies. This upright posture was a significant departure from the sprawling gait of most other reptiles. This upright posture offered immense advantages: greater efficiency in movement, improved speed, and better stamina. It was a subtle but profound innovation that would, over millions of years, enable dinosaurs to outcompete many of their contemporaries and eventually dominate terrestrial ecosystems. The discovery of these early dinosaurs confirmed that their lineage had indeed emerged from the diverse archosaur stock. It wasn't a sudden appearance, but a gradual refinement of features that had been evolving for millions of years in smaller, less spectacular forms. While Aeoraptor and Herosaurus were groundbreaking finds, they didn't immediately signal a dinosaur-dominated world. For millions of years, even after their appearance, dinosaurs remained relatively minor players, sharing the landscape with larger, more established reptilian groups. Their rise was a slow, quiet ascent. Dr. Elena Rodriguez, a specialist in microfossils, focused on even smaller clues. She examined fossilized footprints and coprolites, fossilized droppings, to understand the behavior and diet of these early creatures, revealing aspects of their daily lives that bones alone couldn't. The early Triassic landscape was one of recovery, often hot and arid with seasonal monsoons. Dinosaurs evolved in a world still finding its balance, adapting to fluctuating climates and diverse food sources. Their adaptability was a key to their eventual success. Evolution isn't a race, it's a marathon. For millions of years, different archosaur lines experimented with various body plans, diets, and lifestyles. Some thrived briefly, others faded. The dinosaur lineage was just one of many, quietly refining its blueprint. The recovery of plant life was crucial. As forests of conifers and cycads slowly returned, they provided new food sources and habitats. Herbivorous dinosaurs would later evolve to exploit these resources, while carnivores would prey on the herbivores. While not immediately dominant, the upright posture and efficient locomotion of early dinosaurs gave them a subtle edge. They could move more effectively, perhaps forage over wider areas or escape predators with greater agility. These small advantages accumulated over millennia. Finding these earliest dinosaur fossils is exceptionally difficult. They are often small, fragile, and scattered. Many remain undiscovered, hidden in deep rock layers. Each new find is a triumph, a tiny window into a vast prehistoric past. The search for dinosaur origins is a global endeavor. From South America to Europe, Africa to Asia, researchers scour ancient sedimentary basins, each hoping to unearth the next piece of this grand puzzle. The story is written in stone across continents. Once unearthed, fossils require meticulous preparation. Technicians spend countless hours carefully removing rock matrix from delicate bones, often using dental tools and tiny brushes. This work demands immense patience and a steady hand. After preparation, scientists use comparative anatomy and advanced imaging techniques to reconstruct the animals. This process involves comparing new finds with known species, identifying unique features, and often creating digital models to visualize what these creatures truly looked like. The classification of these early forms often sparked lively scientific debates. Was a certain fossil a true dinosaur or merely a close archosaur relative? These discussions, fueled by new evidence and differing interpretations, are essential to the scientific process, refining our understanding. Some researchers proposed the concept of dinomorphs or dinosauriforms, a group that included the earliest dinosaurs and their very closest non-dinosaurian relatives. This allowed for a more nuanced understanding of the gradual transition. By the late Triassic, around 230 million years ago, the true dinosaurs had firmly established themselves. They were still not the dominant megafauna, but their numbers and diversity were slowly increasing, laying the groundwork for what was to come. Their initial success was a quiet triumph, a testament to subtle evolutionary advantages that proved effective in a world still recovering. They were survivors, adapted to a changing planet, ready for the opportunities that lay ahead. Despite decades of research, the exact moment of dinosaur origin remains a subject of intense study. Each new fossil discovery, each reevaluation of existing evidence, brings us closer to understanding this pivotal chapter in Earth's history. The story of dinosaur origins is a powerful reminder of the patience and perseverance required in science. Millions of years of evolution are compressed into layers of rock, waiting to be deciphered by curious minds. These small, unassuming creatures of the Triassic were the foundation. They carried the genetic blueprint, the anatomical innovations that would eventually lead to the colossal sauropods, the swift raptors, and the mighty tyrannosaurs of later periods. The stage was set. The Permian extinction had cleared the way, and the Triassic saw the quiet emergence of a new lineage. Slowly, imperceptibly at first, the balance of power on land began to shift. As we conclude this first chapter, we've witnessed the humble beginnings, the gentle whispers of a coming era. The next chapter will explore how these small pioneers began to diversify, to grow, and to truly make their mark on a changing world. The journey through deep time is a continuous quest filled with wonder and the promise of new discoveries. We leave the Triassic with a sense of anticipation, ready to witness the unfolding grandeur of the age of dinosaurs. As the Triassic period deepened, the early dinosaurs, those small, agile forms we glimpsed in the previous chapter, were not alone on the ancient supercontinent of Pangaea. They shared the world with a host of other fascinating creatures, many of whom were far larger and more imposing. Among these contemporaries were the pseudosuchians, the crocodile-line archosaurs. These were the true rulers of the mid-Triassic, formidable predators and herbivores that held sway over the land and waterways. Their presence meant intense competition for resources and territory. Dr. Alastair Finch spent years analyzing fossil assemblages from late Triassic sites in North America. His work involved meticulously counting and classifying every bone fragment, every tooth, to understand the relative abundance of different animal groups. It was a quantitative approach to a qualitative mystery. His initial data consistently showed that dinosaurs, while present, constituted a relatively small percentage of the total vertebrate fauna. The larger, more robust pseudosuchians, such as the armored etosaurs and the predatory rauisuchians, dominated the fossil record. This challenged earlier assumptions that dinosaurs immediately rose to power. Instead, it painted a picture of a more complex ecological landscape, where dominance was not a foregone conclusion but a battle fought over millions of years, often in the shadows of established giants. Even the synapsids, the mammal-like reptiles that had dominated the Permian, still clung to existence in the Triassic. Though much reduced in size and diversity, creatures like the small, burrowing cynodonts continued to evolve, demonstrating life's persistent drive to survive. The Triassic world offered a mosaic of ecological niches. Dinosaurs, with their unique upright stance, were beginning to exploit certain advantages. They were often quicker, more agile, and perhaps more efficient at foraging in specific environments than their sprawling competitors. Field expeditions to formations like the Channel in the American Southwest revealed abundant tracks. Dr. Sarah Jenkins, a leading ichnologist, meticulously mapped these ancient footprints, finding a mix of dinosaurian and non-dinosaurian prints telling a story of shared pathways. The trackways showed that while many Triassic archosaurs moved with a sprawling or semi-erect gait, the early dinosaurs left distinct, narrow trackways, indicating their legs were held directly beneath their bodies. This subtle difference was a huge evolutionary leap. This upright posture, however, didn't immediately grant them dominance. The pseudosuchians, with their powerful jaws and robust builds, were still formidable hunters and efficient herbivores. The Triassic was an era of intense, dynamic competition, not a clear-cut victory. The shift to a fully upright posture was a gradual process, not an overnight change. Anatomical studies of early dinosaur skeletons reveal a series of modifications to the hip, femur, and ankle bones that progressively allowed for this more efficient stance. Many early dinosaurs were facultative bipeds, meaning they could walk on two legs but might also drop to all fours. Over time, the advantage of bipedalism, allowing for greater speed, agility, and the freeing of forelimbs, became more pronounced, leading to obligate bipedal forms. Simultaneously, their dentition began to specialize. Early dinosaur teeth were often simple, conical pegs, suitable for a generalist diet. But as they diversified, some developed sharper, serrated teeth for tearing flesh, while others evolved leaf-shaped teeth for processing plant matter. This adaptation of teeth and jaws was a direct response to the available food sources. The recovering Triassic forests and burgeoning insect populations provided a rich tapestry of dietary opportunities, driving evolutionary innovation. With bipedalism, the forelimbs were freed from locomotion. In some lineages, these evolved into grasping hands, perfect for catching prey. In others, they became shorter and stronger, perhaps used for digging or defense. The possibilities were vast. Though difficult to ascertain precisely from fossils, endocasts, internal molds of the brain case, suggested that early dinosaurs had relatively larger brains for their body size compared to some of their reptilian contemporaries, perhaps hinting at increased sensory capabilities or coordination. Recent studies on fossilized lung structures and rib cages have also suggested that dinosaurs developed a more efficient respiratory system, similar to modern birds. This flow-through lung system would have provided a significant advantage in oxygen uptake, especially in a world with fluctuating atmospheric conditions. Microscopic analysis of bone cross-sections, a technique called skeletochronology, revealed that early dinosaurs grew relatively quickly compared to other Triassic reptiles. This faster growth rate could have allowed them to reach reproductive maturity sooner and outcompete slower-growing rivals. Each of these subtle evolutionary innovations, upright posture, bipedalism, specialized teeth, efficient lungs, faster growth, might seem minor in isolation. But together, they created a powerful suite of adaptations that gradually gave dinosaurs an edge in the competitive Triassic world. These advantages, however, were not immediately transformative. For millions of years, dinosaurs remained a part of the diverse Triassic fauna, slowly but surely refining their blueprint, unknowingly preparing for a future that would reshape the planet. By the late Triassic, around 230 million years ago, the first truly recognizable dinosaur groups began to emerge. Among them were the early theropods like Sleepless, a slender, agile bipedal predator. Its fossils were famously discovered in Ghost Ranch, New Mexico. Sleepless was a relatively small dinosaur, typically about 3 meters long, but its sharp teeth and swift movements made it an effective hunter of smaller prey. Its discovery provided clear evidence of early dinosaurian predatory forms, distinct from the larger pseudosuchian carnivores. Alongside the theropods, another crucial lineage was developing, the early sauropodomorphs. These were the ancestors of the colossal, long-necked sauropods, but in the Triassic, they were generally medium-sized herbivores, often facultative bipeds. Plateosaurus discovered extensively in Germany, is a prime example. Growing up to 10 meters long, it was one of the largest animals of its time, characterized by a long neck, small head, and robust body. It represented a significant step towards large-bodied herbivory. The emergence of Sleepless and Plateosaurus demonstrated that dinosaurs were beginning to fill more diverse ecological niches. From agile predators to large herbivores, they were expanding their roles in the Triassic ecosystems, slowly chipping away at the dominance of other archosaurs. Mass death assemblages or bone beds provided further insights. The Ghost Ranch Sleepless bone bed, for instance, suggested that these early theropods might have lived in groups, indicating complex social behaviors not often attributed to early dinosaurs. Fossils of these early diversified dinosaurs were found across Pangaea, from Argentina to Europe. This wide distribution indicated their success in colonizing various environments and their adaptability to different climatic zones. The diversification of herbivorous dinosaurs like Plateosaurus was intimately linked to the flourishing plant life of the late Triassic. Forests of cycads, ferns, and early conifers provided abundant food, enabling larger body sizes and specialized feeding strategies. Even with this diversification, competition remained fierce. Large pseudosuchians still patrolled the rivers and forests, keeping early dinosaurs in check. The Triassic was not yet the age of dinosaurs, but a prelude, a slow brewing of future events. Yet the subtle shift was undeniable. The anatomical advantages, the growing diversity, and the increasing numbers of dinosaurs hinted at a coming change. The foundation was laid, the pieces were in place for a grander act. Then, as the Triassic period drew to a close, around 201 million years ago, a new catastrophe struck. The Triassic-Jurassic extinction event, though less severe than the Permian event, profoundly reshaped life on Earth once more. The exact causes are still debated, but evidence points to massive volcanic activity associated with the breakup of Pangaea. The Central Atlantic Magmatic Province, or CAMP, released enormous amounts of greenhouse gases, leading to rapid climate change and ocean acidification. This environmental upheaval devastated many groups, most large amphibians, many synapsids, and crucially, a significant proportion of the pseudosuchians, the dominant archosaurs of the Triassic, vanished. The world was once again left with ecological vacancies. Remarkably, dinosaurs were largely spared. While some early lineages may have suffered, the core dinosaur groups, including early theropods and sauropodomorphs, passed through the extinction event relatively unscathed. This differential survival is a key mystery. Why did dinosaurs fare better? Scientists propose several hypotheses. Their more efficient respiratory systems, faster growth rates, and perhaps a broader dietary flexibility might have given them an advantage in a rapidly changing world. The extinction of their major competitors, the pseudosuchians, was the critical factor. With the removal of these dominant predators and herbivores, the ecological playing field was suddenly wide open. It was an unprecedented opportunity. The Triassic-Jurassic extinction event didn't just end a period, it ushered in a new one. It cleared the stage, creating the perfect conditions for dinosaurs to truly step into the light and claim their place as the planet's dominant terrestrial vertebrates. It wasn't a sudden explosion, but a quiet, almost imperceptible transformation. The small, agile forms of the Triassic, having weathered the storm, were now poised to diversify and grow in ways that would define an entire geological era. The curtain had fallen on the Triassic, a period of quiet beginnings and intense competition. The stage was now set for the Jurassic, a time when the world would witness the magnificent blossoming of dinosaurian life, from towering herbivores to formidable carnivores. As we close this chapter, we carry with us the knowledge of their patient ascent, their subtle innovations, and the environmental shifts that ultimately paved their way. The next part of our journey will plunge us into the heart of the Jurassic, where the true giants began to walk the earth. The Triassic-Jurassic extinction event had dramatically reshaped the world, leaving behind a vastly altered ecological landscape. Where robust pseudosuchians once dominated, there were now open niches, vast opportunities for any lineage prepared to adapt. Scientists like Dr. Anya Sharma meticulously catalogued the fossil records spanning this boundary. Her work involved comparing species diversity before and after the event, observing a sharp decline in many groups but a curious persistence in early dinosaur forms. It was as if a great reset button had been pressed, clearing the stage for a new act. The evolutionary advantages quietly honed by dinosaurs in the Triassic, their upright posture, efficient respiration, and perhaps adaptability to new food sources, now became paramount. As the Jurassic period dawned, around 200 million years ago, the pace of dinosaur evolution accelerated. The ecological voids were not empty for long. These resilient creatures began to diversify rapidly, filling roles once occupied by others. Fossil discoveries from early Jurassic sites, particularly in regions like South Africa and Europe, began to show a dramatic increase in both the number and variety of dinosaur species. It was a clear signal of their burgeoning success. Among the most striking changes was the emergence of truly large forms. The modest sauropodomorphs of the Triassic began an astonishing evolutionary journey towards gigantism, a path that would define the Jurassic landscape. Paleontologists analyzing bone structure noted a trend towards increased robustness and density in the limb bones of these nascent giants. This was crucial for supporting immense body weight, a key adaptation for their future size. The development of longer necks and specialized teeth for stripping leaves from trees allowed them to exploit new food sources. They became living, walking harvesting machines, transforming vast amounts of plant matter into immense bodies. Simultaneously, the predatory theropods also grew in size and power. As herbivores became larger, so too did their hunters, locked in an ancient arms race that shaped the evolution of both predator and prey. By the mid-Jurassic, the world had truly entered the age of dinosaurs. Terrestrial ecosystems were now dominated by these magnificent creatures, their forms more diverse and specialized than ever before. The sauropods, with their extraordinary long necks and tails, became the undisputed rulers of the herbivorous realm. Brachiosaurus*, for instance, stood like a living tower, its shoulders reaching heights of over 7 meters. The discovery of Brachiosaurus* fossils in the Morrison Formation of North America provided crucial insights into their unique adaptations. Its forelimbs were longer than its hind limbs, giving it a giraffe-like stance, perfect for high browsing. Apatosaurus*, another iconic sauropod, was a creature of immense bulk, known for its powerful tail. Its fossils, often found in bone beds, suggest these animals may have lived in herds, offering protection against large predators. The sheer size of sauropods presented physiological challenges. Researchers studied their bone histology, revealing rapid growth rates, suggesting they reached their enormous sizes relatively quickly, perhaps over decades rather than centuries. Their respiratory systems were likely highly efficient, similar to birds, with air sacs extending into their hollow vertebrae. This reduced their overall weight and provided a continuous flow of oxygen, vital for their massive bodies. The amount of vegetation required to sustain such large animals was immense. Paleobotanists studied fossilized plant remains from Jurassic strata, identifying vast forests of conifers, cycads, and ferns that would have provided this abundant food source. Sauropod trackways, vast trails of fossilized footprints, offered further evidence of their movements and social structures. Some trackways showed adults moving with juveniles, hinting at parental care or herd dynamics. These gentle giants reshaped their environment, clearing vegetation and dispersing seeds, acting as ecological engineers of the Mesozoic. Their presence influenced everything from plant distribution to soil composition. In the shadow of the sauropods, formidable predators evolved. Allosaurus *, the different lizard, was a dominant theropod of the late Jurassic. Its powerful jaws and sharp, serrated teeth made it a fearsome hunter. Fossil evidence from the Cleveland Lloyd Dinosaur Quarry in Utah yielded multiple Allosaurus * specimens, often found alongside sauropod remains. This suggested they were active predators of the large herbivores, not merely scavengers. Studies of Allosaurus * skulls revealed powerful neck muscles and a unique jaw mechanism, allowing them to deliver rapid, hatchet-like bites, causing significant trauma to prey. Their hunting strategy was one of sheer force and speed. The discovery of healed injuries on sauropod bones, consistent with Allosaurus * bite marks, provided direct evidence of these predator-prey interactions. The fossil record told stories of ancient struggles for survival. Some theories propose that Allosaurus * may have hunted in packs, coordinating attacks on larger sauropods, a complex behavior that hints at advanced social structures among these early theropods. Their sharp claws, particularly on their hands, were also formidable weapons used to grip struggling prey. Every part of their anatomy was honed for predation in a world of giants. The mid-Cretaceous saw the emergence of even larger theropods in different regions, like Carcharodontosaurus * in Africa and Giganotosaurus * in South America, demonstrating the continued evolution of apex predators across the breaking continents. Beyond the Titans, other diverse groups of dinosaurs flourished. The ornithopods, often bipedal herbivores, began to evolve more sophisticated chewing mechanisms, allowing them to process tougher plant material. Iguanodon *, known for its unique thumb spike, was an early example found extensively in Europe. This spike may have been used for defense or for stripping foliage from branches. Armored dinosaurs also developed remarkable defensive strategies. Stegosaurus *, with its distinctive plates and thagomizer tail spikes, was an instantly recognizable herbivore of the late Jurassic. The function of Stegosaurus *'s plates has been a long-standing mystery. Theories range from defense and display to thermoregulation, acting as radiators to absorb or dissipate heat. Each theory is carefully weighed against anatomical evidence. The thagomizer, the four-spiked tail, however, left little doubt about its purpose. Fossil evidence of healed wounds on predatory dinosaur bones, matching the shape of these spikes, confirmed its use as a potent defensive weapon. As the Jurassic gave way to the Cretaceous, around 145 million years ago, the armored dinosaurs continued to diversify, leading to the ankylosaurs' heavily armored living tanks with bony clubs at the end of their tails. These diverse forms, from towering sauropods to swift theropods and armored herbivores, showcased the incredible evolutionary plasticity of the dinosaurian lineage, adapting to every available niche. Throughout this golden age, the supercontinent Pangaea continued its slow, inexorable breakup. Continental drift, a powerful geological force, began to isolate landmasses, separating dinosaur populations. This geographical isolation acted as a powerful engine of speciation. Different populations, cut off from one another, evolved independently, leading to unique forms on each continent. For instance, while North America had its Allosaurus ***, Africa and South America developed their own unique large theropods like ***Spinosaurus * and ***Giganotosaurus ***, each adapted to their specific environments. The fossil record from different continents became a tapestry of regional diversity. Researchers found distinct species of sauropods and ornithopods evolving in parallel, showcasing the power of natural selection in varied habitats. Oceanic barriers, once easily crossed on a unified landmass, now prevented gene flow, fostering an explosion of biodiversity. The world became a mosaic of dinosaurian empires, each with its own unique rulers and subjects. By the mid-Cretaceous, dinosaurs had truly reached their zenith. They occupied every terrestrial niche, from towering browsers to agile hunters, from armored defenders to nimble scavengers. Their reign was absolute, spanning millions of years. They had weathered one extinction event, thrived through continental shifts, and evolved into forms of breathtaking variety and scale. The planet was their domain, a testament to their evolutionary success. Yet, even at the peak of their glory, the subtle forces of geological change and the relentless march of time were at play. The stage was set for their ultimate triumph, but also, unknowingly, for a future that would once again transform the Earth, a story we will uncover in our next chapter. Having explored the Triassic origins and the Jurassic ascent of dinosaurs, we now turn our gaze to their daily existence during their golden age. What was life truly like for these magnificent creatures? Beyond the colossal sizes and fearsome reputations, what did their everyday world entail? The fossil record, a silent library of deep time, holds clues not just to anatomy but to behavior. Dr. Ilara Vance, a specialist in trace fossils, spent years studying ancient trackways in regions like the famous Lark Quarry in Australia, seeking patterns in movement. At Lark Quarry, hundreds of small dinosaur footprints are preserved, showing a chaotic scramble. It appears a group of smaller dinosaurs, perhaps ornithopods, fled from a larger predator. This single moment, frozen in stone, hints at dynamic interactions. Further evidence of social behavior emerged from vast bone beds, like the one yielding **Maiasaura** fossils in Montana. Here, researchers uncovered hundreds of individuals, from hatchlings to adults, all buried together. The sheer number and age range of the **Maiasaura** specimens suggested these duck-billed dinosaurs lived in large herds, migrating across ancient floodplains. This communal living offered protection and shared resources. But the **Maiasaura** site revealed something even more profound: evidence of parental care. Nearby, nests were found with fossilized eggs and even young dinosaurs, too large to be hatchlings, suggesting they stayed in the nest after birth. This was a revolutionary discovery. It challenged the long-held view of dinosaurs as solitary, uncaring reptiles. Instead, it painted a picture of nurturing parents dedicated to their offspring's survival. The name **Maiasaura** itself means good mother lizard. Communal nesting sites where multiple nests were found close together indicated that some dinosaurs gathered to lay their eggs, perhaps sharing duties or benefiting from the collective defense against predators. Other fossil evidence, like the elaborate crests of Lambeosaurine hadrosaurs, hinted at complex visual and auditory communication within herds. These hollow crests may have amplified calls or served as visual displays for mates. These findings transformed our understanding. Dinosaurs were not merely large, instinct-driven beasts, but creatures capable of sophisticated social structures, parental bonds, and complex communication, much like modern birds or mammals. The daily lives of dinosaurs were also defined by the relentless cycle of predator and prey. Scientists meticulously analyzed skeletal adaptations, teeth, and claw marks to reconstruct ancient hunting strategies and defensive measures. Apex predators like Tyrannosaurus rex possessed immense bite forces, estimated to be among the strongest of any terrestrial animal. Their robust skulls and powerful jaws were built for crushing bone, not just tearing flesh. Evidence from bite marks on fossilized bones, particularly on large herbivores, showed that T. rex was an active predator. Some marks indicated successful kills, while others suggested scavenging, pointing to a versatile hunter. In contrast, smaller, agile predators like dromaeosaurids or raptors likely hunted in groups. Their sickle-shaped claws and keen senses would have allowed them to subdue prey larger than themselves through coordinated attacks. The herbivores, in turn, developed remarkable defenses. The ceratopsians, like Triceratops were equipped with formidable frills and horns, acting as both defense against predators and possibly for intraspecies combat. The ankylosaurs, true living tanks, were covered in thick, bony armor, with some species possessing a heavy club at the end of their tail. This was a direct response to the powerful predators they faced. Studies of the brain cases of ankylosaurs suggest a highly developed sense of smell, vital for detecting predators, while their low-slung bodies allowed them to graze peacefully, protected by their natural fortifications. Even the colossal sauropods relied on defense. Their immense size alone was a deterrent, but their powerful, whip-like tails could deliver devastating blows, as evidenced by healed injuries on the tailbones of some individuals. Coprolites, fossilized droppings, provide direct insight into dinosaur diets. Analysis of plant fragments in herbivore coprolites reveals their specific food sources, while bone fragments in carnivore coprolites confirm their predatory habits. The Mesozoic was a dynamic arena, a constant struggle for survival. Each adaptation, whether for hunting or defense, was a testament to millions of years of evolutionary pressure, shaping the giants of the past. Beyond external appearance and behavior, scientists sought to understand the internal workings of dinosaurs, their physiology. Were they cold-blooded like modern reptiles or warm-blooded like birds and mammals? This question sparked decades of debate. Bone histology, the study of bone microstructure, provided crucial clues. By examining cross-sections of dinosaur bones, scientists observed patterns of rapid growth, similar to fast-growing mammals and birds, suggesting high metabolic rates. Oxygen isotope analysis of fossil bones also offered insights. The ratio of different oxygen isotopes can indicate body temperature stability. Some studies suggested dinosaurs maintained relatively stable internal temperatures, a hallmark of endothermy. The sheer size of many dinosaurs presented its own physiological challenges. For sauropods, gigantism itself could have helped maintain a stable body temperature due to thermal inertia. A large body heats and cools slowly. Reconstructing their senses required examining the internal structures of fossilized skulls. Endocasts, natural or artificial molds of the brain cavity, revealed the size and shape of different brain regions. The olfactory bulbs responsible for the sense of smell were often very large in many theropods, suggesting a keen sense of smell was crucial for hunting or scavenging. Their world was rich with scent. The structure of the inner ear, particularly the semicircular canals, could offer clues about head posture and agility. Some dinosaurs had inner ear structures optimized for rapid head movements, indicative of active lifestyles. While intelligence is difficult to gauge from fossils, the relative brain size to body size in some smaller theropods, like troodontids, suggested a degree of cognitive complexity, perhaps even problem-solving abilities. Estimating growth rates from bone rings, similar to tree rings, showed that many dinosaurs grew incredibly fast during their juvenile stages, reaching enormous sizes in a fraction of the time modern reptiles would take. These physiological insights painted a picture of active, dynamic animals, far removed from the sluggish, cold-blooded reptiles once imagined. Their internal lives were as complex and varied as their external forms. Perhaps one of the most revolutionary discoveries challenging our very perception of dinosaurs was the widespread presence of feathers. For a long time, feathers were considered unique to birds. The initial breakthrough came from the Liaoning province in China, with fossils like Sinosauropteryx**. This small theropod was found with a clear halo of filamentous structures around its body, undeniable proto-feathers. This discovery and many others that followed confirmed that feathers were not an exclusive avian trait but originated much earlier, within the dinosaur lineage itself, long before flight evolved. These early feathers were not for flight. Instead, they likely served functions like insulation, helping to regulate body temperature in these active, warm-blooded animals, or for display, attracting mates or intimidating rivals. The revelation of feathered dinosaurs meant that many familiar theropods, from small raptors to even some larger tyrannosaurs, might have been covered in a downy coat or bristly filaments, not bare reptilian skin. For instance, evidence suggests that juvenile *T. rex* may have had a covering of downy proto-feathers which might have been lost as they grew larger, similar to how large birds like ostriches have reduced plumage. This discovery fundamentally changed our visual image of dinosaurs, making them more dynamic, more bird-like, and even more wondrous. It revealed another layer of their sophisticated biology. The daily lives of dinosaurs were a tapestry woven with complex social structures, fierce battles for survival, intricate physiological adaptations, and the surprising beauty of feathers. They truly mastered their world. From the quiet rustle of a feathered predator to the thunderous steps of a sauropod herd, life during the Mesozoic was vibrant and dominant. Dinosaurs had truly carved out an empire that spanned continents and millennia. Yet, even the most magnificent empires eventually faced their challenges. As the Cretaceous period neared its end, forces beyond their control were gathering, forces that would test the very resilience of life on Earth. We will explore this ultimate challenge in our next chapter. The Cretaceous period, for all its vibrant life and dominant dinosaurs, was not an unchanging canvas. Beneath the surface of flourishing ecosystems, subtle shifts were already at play, hints of a world under increasing strain. For millions of years leading up to the final act, Earth's climate had been subject to fluctuations. Scientists studying ancient sediment cores observed subtle but consistent changes in ocean chemistry and atmospheric composition. One significant factor was massive volcanic activity, particularly in a region now known as the Deccan Traps in India. These eruptions were not single events but prolonged, intense outpourings of lava over hundreds of thousands of years. Imagine colossal rivers of molten rock flowing across vast stretches of land, building up layers upon layers of basalt. The sheer volume of lava released was staggering, covering an area larger than modern-day France. These eruptions spewed enormous quantities of gases into the atmosphere: carbon dioxide, sulfur dioxide, and other aerosols. Such emissions would have had profound, long-term effects on global climate. Initially, carbon dioxide could have led to periods of global warming, but sulfur aerosols would have reflected sunlight, causing temporary cooling events, creating a volatile and unpredictable climate. The continuous influx of these gases also altered ocean chemistry, leading to acidification. Marine organisms, particularly those with calcium carbonate shells, would have struggled to survive in these changing waters. Paleontologists noticed a decline in diversity among some marine invertebrate groups in the fossil record leading up to the KPG boundary. This suggested ecosystems were already under stress long before the final cataclysm. So, the world of the late Cretaceous was not entirely tranquil. It was a planet already grappling with significant environmental pressures, a canvas stretched taut, perhaps more vulnerable to a sudden, devastating shock. These volcanic events, though immense, were likely a slow burn, weakening the global ecosystem. But the final, swift blow came from an entirely different source, a force from beyond our planet. For decades, scientists pondered the abrupt disappearance of non-avian dinosaurs. The idea of an extraterrestrial impact, once considered radical, began to gain traction in the late 20th century. The pivotal moment arrived with the work of Luis Alvarez, a Nobel laureate physicist, and his son Walter, a geologist. They were studying a specific clay layer marking the end of the Cretaceous period in Gubbio, Italy. They were looking for a way to measure the rate of sedimentation using iridium, a rare element on Earth but relatively common in meteorites. Their findings, however, were entirely unexpected. At the Cretaceous-Paleogene boundary, the iridium levels were astonishingly high, hundreds of times greater than normal background levels. It was a global anomaly, a signature that couldn't be explained by earthly processes alone. This iridium spike led the Alvarez team to propose a daring hypothesis. A massive asteroid or comet, perhaps 10 to 15 kilometers wide, had struck Earth, causing the widespread extinction. The hypothesis was met with skepticism. Where was the crater? Such an immense impact should have left an unmistakable scar on the planet's surface. The search began for this colossal wound. Decades later, evidence converged on the Yucatan Peninsula in Mexico. Geophysical surveys revealed a vast, circular subsurface structure, the Chicxulub crater, hidden beneath layers of younger sediment. The crater, measuring approximately 180 kilometers in diameter, perfectly matched the predicted size for an impactor capable of creating the global iridium layer. The energy released was equivalent to billions of Hiroshima bombs. When the asteroid struck, it wasn't just an explosion. It was an instantaneous vaporization of rock, creating a superheated plume that shot into space, carrying dust and debris far above the atmosphere. This ejected material, including melted rock droplets called spherules and shocked quartz crystals, rained down globally, providing further physical evidence of the cataclysmic event. The impact plunged Earth into an impact winter. Dust and soot from widespread fires ignited by the searing heat of the impact blocked out the sun, turning day into an eternal twilight. Global temperatures plummeted, photosynthesis ground to a halt, and much of the plant life died. The base of the food chain collapsed almost instantly. The sheer energy of the impact, combined with superheated ejector raining back down, ignited continent-spanning wildfires. Forests that had stood for millions of years were incinerated in moments. Vaporized rock and atmospheric gases combined to create massive acid rain. Oceans, already stressed by volcanic activity, became even more acidic, devastating marine life from the top to the very bottom of the food chain. The impact also generated colossal tsunamis hundreds of meters high that scoured coastlines thousands of kilometers away. Massive earthquakes rocked the planet, adding to the immediate devastation. These combined forces created an unprecedented ecological collapse. The interconnected web of life, built over millions of years, unraveled with terrifying speed. Non-avian dinosaurs, the dominant life forms for 160 million years, were particularly vulnerable. Their large sizes, long lifespans, and specialized diets meant they could not adapt quickly enough to the sudden, drastic changes. Smaller, more adaptable creatures capable of burrowing, scavenging, or surviving on seeds and detritus had a better chance. Mammals, birds, avian dinosaurs, crocodiles, and some reptiles found ways to endure the global winter. The KPG boundary layer, with its iridium, shocked quartz, and soot, represents one of the clearest and most dramatic geological markers of mass extinction. It is a stark dividing line in Earth's history. This was not a localized event. The evidence for the impact and its devastating consequences has been found in rock strata all over the world, from deep ocean cores to terrestrial outcrops on every continent. The most striking aspect of this extinction was its rapidity. While the Deccan traps may have caused a slow decline, the asteroid delivered a sudden, lethal blow from which the dominant dinosaurs could not recover. And so, the reign of the magnificent non-avian dinosaurs came to an abrupt and violent end. Their era, a golden age spanning 3 geological periods, concluded in a single, catastrophic moment. The silence that followed the initial chaos must have been profound. A world that had echoed with the roars of predators and the thunder of herds was suddenly quiet, scarred, and forever changed. The immediate aftermath was a period of darkness and extreme conditions, but life, in its tenacious way, would slowly begin the arduous process of recovery, finding new footholds in the devastated landscape. The rocks themselves hold the story of this transformation. From the oldest Triassic whispers to the final Cretaceous roar, they are a testament to life's grand narrative, its triumphs and its ultimate vulnerabilities. Unraveling this story required generations of scientists, each adding a piece to the puzzle. Geologists mapping layers, paleontologists unearthing bones, chemists analyzing elements, and physicists modeling impacts. The impact theory, once a bold idea, now stands as the most widely accepted explanation for the KPG extinction, supported by an overwhelming body of evidence from across the globe. This event serves as a powerful reminder of Earth's dynamic nature and its susceptibility to extraterrestrial forces. It highlights how swiftly dominance can shift and how fragile even the most established ecosystems can be. The final act of the dinosaurs was a dramatic conclusion to an extraordinary reign, but every ending is also a beginning, and the ecological vacancies left by their departure would pave the way for new forms of life to flourish. As the dust settled and the planet slowly healed, a new chapter of life was ready to unfold. The small, unassuming survivors of the KPG extinction would inherit a transformed world, setting the stage for the rise of entirely different giants, a story we will explore in our final chapter. The great impact had silenced the roars, but not all life vanished. In the scarred, recovering world that followed the cataclysm, a quiet miracle unfolded among the survivors. Among those who endured were small, feathered creatures, the avian dinosaurs, whose lineage had already begun its evolutionary journey long before the asteroid struck. Their unique adaptations for flight, their smaller size, and perhaps their diverse diets gave them an unexpected resilience in a world turned upside down. While many bird groups of the Mesozoic did perish, a few tenacious lineages managed to cling on, finding refuge in pockets of surviving vegetation or scavenging on what little remained. From this severe evolutionary bottleneck, a new radiation began. The empty skies and nascent forests were ripe for colonization, and these avian survivors were poised for a new chapter. Over millions of years, these surviving bird lineages rapidly diversified, evolving into the incredible array of forms we see today, from soaring eagles to diving penguins. Modern birds are not just related to dinosaurs, they are dinosaurs. They are a constant, vibrant, and living reminder of that ancient, majestic lineage that once ruled the earth. Comparative anatomy reveals the striking similarities in their skeletal structures: hollow bones, fused clavicles, the wishbone, and specialized respiratory systems, all echoes from their deep past. And the feathers, once thought to be unique to birds, are now known to be a dinosaurian invention, appearing much earlier in their evolutionary history, initially for insulation or display. Their continued success, spanning continents and climates, is a testament to the incredible resilience and adaptability of the dinosaurian blueprint. But the KPG event also opened the door for another group that had long lived in the shadows: the mammals. For 160 million years, they had been small, mostly nocturnal creatures. Their small size, warm-bloodedness, and often burrowing lifestyles proved advantageous during the impact winter. They could shelter underground, survive on seeds or insects. With the giants gone, a vast array of ecological niches lay vacant. The world, once a dinosaurian empire, was now an open canvas for new forms of life to fill. Over the next millions of years, the Cenozoic era, known as the Age of Mammals, saw an explosion of new forms, rapidly adapting to the changed environment. From tiny shrews, they evolved into colossal whales, swift gazelles, and eventually the large terrestrial herbivores and carnivores that would come to dominate. This dramatic shift in dominance underscores a profound lesson. Extinction, while devastating, is also a powerful engine of evolution, reshaping the tapestry of life. It is within this mammalian radiation that our own lineage emerged, a direct consequence of the great dinosaurian extinction event. We owe our existence to that ancient cataclysm. The world we inhabit today, with its diverse animal life, is a direct legacy of those two great survivor groups, the birds and the mammals, forever linked to the dinosaurian past. Yet, the story of dinosaurs is not confined to ancient rock layers. It continues to unfold in laboratories and field sites around the globe, driven by an insatiable human curiosity. New fossil discoveries are made almost yearly, each one adding another piece to the intricate puzzle. From feathered dinosaurs in China to colossal sauropods in Argentina, the Earth still holds countless secrets. Modern paleontologists employ advanced techniques far beyond the picks and brushes of earlier generations. Ground-penetrating radar helps locate buried fossils without extensive excavation. In the lab, CT scanning allows scientists to peer inside fossilized bones, revealing internal structures, brain cavities, and even soft tissue impressions without damaging the precious specimens. Molecular paleontology, though challenging, seeks to extract and analyze ancient proteins like collagen from exceptionally preserved fossils. These tiny fragments offer direct chemical links to the distant past. Biomechanical studies use computer modeling to simulate dinosaur movements, bite forces, and even vocalizations. This brings these ancient giants to life, helping us understand their capabilities and limitations. Beyond individual animals, scientists reconstruct entire ancient ecosystems, piecing together plant life, climate data, and predator-prey relationships to paint a complete picture of their world. This global effort involves researchers from diverse fields, geologists, biologists, chemists, and physicists, all contributing to the grand narrative of deep time. Every new piece of evidence, every re-examination of old bones, refines our understanding. Theories are tested, debated, and sometimes overturned as the scientific process continually sharpens our view of the past. The story of dinosaurs is a testament to the power of scientific inquiry, a relentless pursuit of knowledge, driven by observation, experimentation, and collaboration. Despite immense progress, many questions remain. The colors of their skin, the specifics of their social calls, the exact nuances of their intelligence, these continue to inspire new research. The journey of discovery is endless. Each generation of scientists builds upon the last, deepening our connection to these magnificent creatures and the world they inhabited. Beyond the scientific quest, dinosaurs hold a unique place in the human imagination. From childhood wonder to cinematic spectacles, they are symbols of awe, power, and a lost world. They continue to inspire new generations, sparking curiosity about science, evolution, and the incredible history of our planet. They are our prehistoric ambassadors. They teach us about deep time, about scales of existence almost impossible to grasp. Their 160 million year reign dwarfs the mere blink of human civilization. They are a profound lesson in evolution itself, the slow, patient accumulation of adaptations, the branching of lineages, and the incredible diversity that can arise from simple beginnings. And they are a stark reminder of Earth's dynamic nature, its vulnerability to cosmic forces, and the cyclical pattern of life and extinction that has shaped our planet for billions of years. Their story reminds us that even the most dominant forms of life can be swept away, highlighting the delicate balance of ecosystems and the constant flux of our planet. The mystery of their rise and fall, once shrouded in myth, is now illuminated by scientific endeavor. We understand not just asterisk that asterisk they vanished, but asterisk how asterisk and asterisk why asterisk. Yet even with all our knowledge, a profound sense of wonder persists. What was it truly like to walk among them? What sounds did they make? These questions keep the prehistoric magic alive. From their quiet Triassic origins through their Cretaceous triumphs to their ultimate demise, the dinosaurs offer a complete saga of life's journey on Earth. Their echoes resonate through time, a timeless whisper reminding us of Earth's incredible past and its endless capacity for renewal. And so, as the moon climbs high, sleep well and let the wonders of deep time fill your dreams.